All right, here's day 2 of the limits section here. Hopefully this can clear up some things from yesterday's notes and help you guys a little bit here. Again, remember, you can always join me on the Zoom sessions if you have any questions and you need some one-on-one assistance. So here's kind of a review from what we did last couple days here, looking at a graph here if we wanted to evaluate. So if we were going to evaluate this function here, first thing, obviously, we can factor this. And when we do that, then we end up getting a function that would look like f of x equaling 1 over x plus 2, which is why the graph looks the way it does, where it has an asymptote at -2, right? So we have a VA at -2, because that's what makes it equal to 0. And we have a hole, though, here. Remember, this is a hole in the graph, right? HIG, a hole in the graph, at x equals 1, which we see right here. So if we look at this graph here now, so basically what we learned from yesterday is we're really going to have two places where limits, where we could have a problem with limits. Or one place, actually. The one place would be right here, where we have an asymptote. So really only at that asymptote where the limit not exists. Everywhere else the limit's going to exist, because if you have a hole, you would end up, if you approach that hole, you're approaching the same spot, so the limit would exist. So if we were to evaluate these functions here, basically if we wanted to find f of -3, we can literally just plug in -3 into the original function and get -1. Or we can make it a little bit easier on ourselves, since we simplified it here to be this. If we plug that in, we can go 1 over -3 plus 2, and we would get the same answer, 1 over -1, which is -1. So the way I'm getting these solutions here, I can plug it into the original or into the simplified version. The problem is here, if we plug part B here into the simplified version, so look, if you plug it into the original, we get it undefined, because -2 is where we have our asymptote. This is where our vertical asymptote exists. So that's why it's undefined. However, if we try that for 1, well, if we plug 1 into the original, we're going to get it to be undefined. But if we look back up here, 1 is where the hole happened. So actually, if we plugged 1 into the reduced version, we get 1/3. And if you look over here at the graph, that's approximately where it's going to be at here. That would be the point 1 and 1/3. That is not the evaluated function, so this is not the answer. The answer here is it's undefined, because you don't have a point there, because x cannot equal 1. But we'll come back to that, and I'll explain what I'm talking about there later. The limit would be at that 1/3. If you want to evaluate 4, we can just literally plug 4 in and we get 1/6. Again, you can plug it into the original, or you can plug it into the simplified version. The simplified version is just a lot easier. If you look at it here, it's a lot easier to complete. All right, so if we want to determine the limits, remember, if we're determining limits, this is a two-sided limit here. So the limit of f of x as x approaches -3. So as we approach -3, if we look over here, -3 is right here. So we don't have a problem here. There's no asymptotes, there's no holes, there's no jumps. So we should be fine here. We just have to find the value right here that we have, because we're from the left, we approach that value of -1. And that's what this is saying right here. From the left, we get -1. From the right, we also get -1. Right? So they both approach -1. Remember, we have to ask both of these questions. Both of these questions have to be asked in order to answer the original question of the limit as f of x approaches -3. And that would be -1, because these happen to be the same. So we look at the next one. The next one says here, the limit as x approaches -2. -2, right, is where we have an asymptote. So since we have an asymptote there, look, as we approach from the top and the bottom, as we approach from the right here, we're going up to positive infinity. So as we approach from the right, we're going to positive infinity. As we approach from the left, we go down to negative infinity. Since these here are different now, we say the limit does not exist because it does not approach the same value from both sides. And that's because there's a vertical asymptote. Like think of, again, there's a VA here at x equals -2. And that's typically where we're going to have a limit won't exist at vertical asymptotes. There are some rare occasions where it does, but most of the time it does not exist when you have an asymptote. So if you look at the next one. The limit as x approaches 1. We'll look over here. 1 is right here. So now 1 has a hole. But as we approach 1 from the right, look at where we're going to. We're going to that hole right there. We approach from the left, we're going to the hole. So we're going to the same spot. Now what is that spot we're going to? That spot is the spot we figured out before, which is 1 over 1 plus 2, which is 1/3. We did that up here before evaluating C when we did the simplified version. There's a hole in the graph, so the point doesn't exist, but we do approach the same value, and that value is 1/3 because we approach the same value from both sides. So things to note here now. This is the key kind of the limits here. If you have a graph, limits do not exist where you have an asymptote or a jump. If you have a hole, the limit does exist, and the limit is where the simplified version is. And that's what we're going to work on today. And that's what this all says right here. So if you look at parts A and E, if the point exists, just plug it in, and that's where the limit exists there, and it is that point. If the point does not exist, or if there's an asymptote, a vertical asymptote for instance, then the limit does not exist, and you'd have to look at the kind of graph to prove that, but the limit would normally not exist there. If there's a hole in the graph, the point does not exist, but the limit does, and the limit is where the hole happens. So now if we don't have a graph, this is how we have to do it here. So our steps for evaluating based off of that information here. If we ever want to evaluate limits, these are our steps. You're simply going to simplify the function, and then if you can plug in the value for A, meaning where the limit is going. If you can't plug it in, if it has a vertical asymptote at that value of A, then you either look at the graph or we have to do some more investigation where we test some points. And we'll see some problems here as we go. So first, the easiest of easy. Here, this is a continuous function. If you can plug that value in, then you plug it in. So all we simply do is plug in -3 in for x. This value does exist. 9 plus 9 is 18, and that's where the limit is at 18. Same thing here. The only value that does not exist, we can have, x cannot equal 2 because you cannot have the denominator equal 0, but this is not 2, so you can simply plug this in. So if you plug it in, your value ends up being -6 plus 4, -2 over -5, or +2 over 5. But all you do is you plug it in. So simplify if possible. Neither one of those simplified, but if you can plug it in, then you plug it in. Now the problem is if you can't plug it in. So here, notice if I threw 0 in right here, it would become undefined because x cannot equal 0. So I have to do more work beforehand. So before I plug it in, I need to simplify, and that's why it's always the first step is to simplify. Here, I can cancel out an x from everything to get the new function 4x minus 7 over 2. Now I can plug 0 in to get 4 times 0 minus 7 over 2. And I have no problem here, so I end up getting -7 over 2, and that's what my limit would be. So I had to simplify before I could just plug in the value for A. Same thing goes here. If I simplify here, I can factor the top. Now that cancels because, again, x cannot equal -5 here because that would make it 0. But since it canceled, now when I plug in the -5 here, I get -5 minus 5 to get -10 as my limit. So again, we simplify when possible, and then just simply plug it in. That's how easy limits can be if we understand the factor that we just simplify and then plug in. If we plug it in, we should get a value out. If we get a value out, then that is our limit. Now, the problem happens if you plug it in, you get undefined, or if the function is asking for a one-sided limit and it has a vertical asymptote. So if a function is undefined when you plug it in, that means you're approaching the vertical asymptote. Right? So if you're approaching a vertical asymptote, you need to look at the graph. So you need to look to tell, is the curve going up or is it going down? You can do it you can look at a graph, or we can do some more investigating by plugging in, testing, like we can test values to the left and the right and to see where is our graph going. Is it going up or going down? And I'll do some examples as we go here. So we look at this first one here. This is a one-sided limit, and we're coming from the right here. So as we approach 2 from the right, notice 2 is our vertical asymptote here because x cannot equal 2. So that's our vertical asymptote. Right? So that's why it's a problem. We can't plug 2 in. If we plug 2 in, we get undefined. So we can look at the graph. And if we look at the graph from the right, our graph would show us that it goes up, which is why the answer here says infinity. Now, the other way you can do it if you don't want to look at a graph, if you don't plug it in your calculator, you can test the value. So you would have to test the value to the right of 2. You can test any value you want to the right of 2. For instance, let's test the value 3. So if you test 3, you plug 3 in. You get 1 over 1. 1 over 1 is a positive number. And if it's positive, that means the values are going up. And that if they're going up to infinity. Because positive values would only go up because of the horizontal asymptote. You would have to stay above the horizontal asymptote, which is why we're going to infinity. So we could do this algebraically by testing a value if we didn't want to plug it into a calculator. Here's another example. Again, here, right, we can't get this to equal 0, so x cannot equal 5. So we have a VA at 5. So that's our vertical asymptote, right? So since that's the value that we're checking here, we can't just plug it in. So we have to then look at the graph. So if we look at the graph here, this one's saying from the left now. So we look from the left, this one's going up again, so it's going up to infinity. Or we could test the value to the left of 5. Now, the easiest value to test to the left of 5 would be 0, a value smaller than 5. So if you threw in -3, 0 minus 5, you get a -3 over a -5, which again is a positive value. I don't care about the numbers, it's a positive value. Since it's positive, it means it's going up to infinity. So our answer here would be to infinity. We're testing the values here. Remember, test any value you want, to the left or to the right, depending on what the question's asking. All right, and now for our fourth and final type of limits here that we have to evaluate are limits that have x going to positive or negative infinity. If x is going to positive or negative infinity, we're talking about end behavior. Now when we talk about end behavior, we're talking about, is it an even or odd function, and is it positive or negative? Remember, even functions both go up or down. Odd functions, one goes up, one goes down, like that here from our end behavior quiz and worksheets. Or if it's a fraction, then we're talking about our horizontal asymptotes. So here's 2 examples. So here, again, since we're like here, immediately because it says x is going to infinity, we're talking end behavior. So since we're talking end behavior, we look here. We look at this function. We're looking at the highest power here. That's an odd function because it has an odd power. That's an odd positive. So if it's odd positive, that means it goes up to the right to the positive infinity, goes down to negative infinity here. So as we say here, as x goes to infinity, infinity is positive, so that means as we go to the right, where are we going? We're going to positive infinity as we go to the right. For here, this next one, now this one's a fraction, so since this one's a fraction, we're looking at our HA. All right, so that will tell us here whichever way we're going. So our HA here, well, the bottom is bigger. Remember, horizontal asymptotes, top, bottom are the same. If the top's bigger, we have to look at the graph. If the bottom is bigger, then it just goes to 0. If they're the same, we take the ratio of the coefficients. Here, the bottom is bigger. So then we know it's going to 0. the horizontal asymptote is 0. And that would be your limit then. Basically, this graph, what this graph would look like here, is this graph would have something, it would be leveling off at the value of 0. All right, so here's a number of examples here of how to do what those 4 types we have. And those are really the only 4 types. So notice here, 1 through 4, I have already done for you, because 1 through 4, each of the numbers that are given there, like 1, you can just simply plug it in. So we just plugged it in, and we get our answer of -1. -5, you can plug -5 in here, because you plug in -5. Even though you get 0, the value is still 0. It's not undefined, it's a value, so it's a value of 0. So if you can plug in a number, even like pi, even though pi is just an irrational number, you can plug pi into both of these here. So when you plug pi in, you get 1 over pi, and that would be where your limit exists. If you plug in 0, same thing, just plug 0 in. There's no problem here. You get a value out, so it's -2. So 1 through 4 was the simple ones here. If you can plug it in, plug it in. It brings me back to the old Glad commercials. Plug it in, plug it in. If you can plug in the function, plug it in. Now, for problems like this here where you have to do a little bit more work, you cannot plug in -3, because here you can't, x cannot equal 3. So you can't plug it in right away. So you have to do a little bit more work. So simplify. So we simplify by factoring. Now those factors cancel. So now the factors cancel, so we're left with x plus 5. So now we can plug 3 in to get 8. And so our answer here, our limit would be 8. So we just simplify and then plug in after we're done. So here again, simplify. So we got values of 10, factors of 10 that add up to -3. So we get x minus 5, x plus 2. We got to divide both of these by 2. So we get the factors of 2x minus 5 and x plus 1 all over x plus 1. We can cancel out x plus 1, so now we can plug it in. So 2 times the -1 minus 5 gives us -2 minus 5, which is -7. So our limit here would be -7, because we had to plug in -1. Some of this might look familiar here. This is what we were basically doing during our review sessions, then our end behavior sessions, and our continuity sessions. We're doing a bunch of this stuff here. So like this one here, if you can remember now, if we have x minus 9 and we have a root somewhere, we can cancel that root out by simply taking the factors, because these are perfect squares, of root x minus 3 and root x plus 3 of x minus 9. So now we can cancel out the root x minus 3, and we get root x plus 3 left over. So root x becomes root 9 plus 3 by plugging in that 9. So root 9 plus 3 is 3 plus 3, which is 6. Again, here you see something like this. Here you've seen this before. Just distribute. You get -2x minus 2h plus 2x all over h. Notice the 2x and 2x cancel. And then the h's actually cancel, so you're left here with just -2. So it doesn't matter what it says h goes to here, or whatever value we're saying we'll go to. This only can go to -2. So again, so 5, 6, 7, and 8 are all examples of where you had to simplify first before you could plug it in. So then 9, 10, 11, and 12 here now are the more complicated ones here, where we either have to test the value or look at the graph. Notice most of these are going to be one-sided limits. So here again, we have a vertical asymptote at -1, which is the problem. We can't plug in that value of -1. So we could look at the graph. It says from the left, right? Because it says from the negative side. So if we come from the left, you can see the graph says that we're going down. So our answer here we could say is -infinity. Now that's one way to do it. The other way to do it would be testing a value. A value to the left of -1 is -2. So if you threw in -2 into the function, you get 1 over -1, which is a negative. Now, it's a negative value, which means it's going down, and where is it going down to? -infinity, which is why we got our answer of -infinity. You're just looking at if it's positive or negative for your test value, and if it's negative, it's going down to -infinity, and if it's positive, it's going up to +infinity. Look at example 10. Example 10. Notice we can factor this here and simplify it so we actually can cancel out these x plus 2's, but we still have a vertical asymptote at 3. So the value that's in question is 3, so we have a problem with that because we can't plug 3 in. We would get undefined. So we're going to test the value here. So we test the value to the right because it says positive there. So to the right of 3 is 4. So we threw a 4 in. So 4 minus 2 over 4 minus 3 gives us 2 over 1, which is a positive value. Since it's positive, we know it's going up. Where's it going up to? Positive infinity. And again, if you want to use the graph, you can look at the graph and see that the graph goes up as well. Number 11. Again here, so now this one here, it's a two-sided limit. It says x, as x approaches -5, and it doesn't have a plus or minus in the power form. So therefore, we have to check both sides, which is why here I tested both the left and the right side. So if you were testing both the left and the right side, you would test in a value to the left of -5, such as -6. You would get a negative value out, which means it's going down to negative infinity. Then you would have to test the value to the right of -5, such as 0, for instance, is to the right of -5. When you plugged in 0, you get a positive value, which means it's going up to positive infinity. Since these are different, remember, from yesterday and the day before, since those are different, we then say that the limit does not exist. Your Mean Girl reference. Right? We can also look at the graph and see, okay, yeah, from the right it goes up, from the left it goes down. They do not go to the same place, therefore the limit does not exist. Remember, they have to have the same values for the limit to exist. Typically, if you have a vertical asymptote and it's a two-sided limit, most of the time the limits will not exist at a vertical asymptote unless it's a one-sided limit. So we look at the next one here, same thing. We can factor this and factor this. Our x plus 2's cancel. That was the problem in question. So now we can just simply plug it in. So if we plug in now -2, we get -4 over -5, and that's a value. So we actually get our answer right there to be a +4 over 5. Remember, the only problem is if you can't plug that value in, then it becomes undefined is when you have an issue. If you can plug it in, plug it in. And then now for the fourth set. The fourth set here are all when we have x going to positive or negative infinity. So now we're talking about end behavior. So here, since it's x going to negative infinity, we're looking at our highest power there, which is here our highest power is odd, and it's negative. So if it's odd negative, it's going down to the right. So it looks like that. So as we go to, this is asking as we go to the left, where we're going was we go to the left, we're going up to positive infinity. For 14, this one here is asking as we go to the right. It's a fraction now, so if it's a fraction here, we're looking at our horizontal asymptote. What is our horizontal asymptote? Well, here, the powers are the same. So since they are the same, we take the ratio of the coefficients, which would be 8 over 4, and 8 over 4 equals 2. And so it would level off at 2, and that would be what our end behavior is, our asymptote, and therefore our limit. 15. Here now, this is one of the tougher ones here. So again, we notice we're looking for our end behavior. Here, the top is bigger. So now we can look at a graph. You can look at the graph in your calculator. And if you looked at the graph, you would get something that would look like this as you went to the right. Or you can do a quick simplifying problem. So you could take the x to the fourth over 2x squared and simplify it real quick and get up x squared. Well, since it comes out to be a positive even function, we can also say that it's opening up both sides, which means we're going up to positive infinity. So you can do that two methods too. Here's a lot of examples here, and this is kind of the main focus of this chapter here, and what we're finishing up with here before our test is limits. Right? So if you can plug it in, right, 1 through 4, plug it in. If not, simplify 5 through 8, simplify before you can plug it in. Now, if you're talking about vertical asymptotes like 9 through 11, if it's a vertical asymptote, you need to test the value or look at a graph from the sides that they're coming from. And then last but not least, if it's going, x is going to positive negative infinity, then we're talking about end behavior. all things here and why we spent so much time on reviewing factors and all the other things we've been doing before this, because it all comes in play now while we do our limits. Again, you always can come visit me in our Zoom sessions here. Haven't seen faces in a while, so it'd be nice if some of you guys could come join me, ask some questions, or just check in and let me know how you're doing. Hope you're staying healthy and be well.